Okay, so before we see the exercise though, there is a small definition. It's the definition of a diagonal matrix which all of us most probably know. So a diagonal matrix A whose ith row jth column entry is alpha ij is a square matrix such that all the off diagonal entries are 0. That means all the alpha ij are 0 for I not equal to j. The definition does not say anything about the diagonal entries though, they may or may not be 0. And then such a matrix or a linear transformation is said to be diagonalizable. If the matrix is similar to a diagonal matrix, then the matrix will be called a diagonalizable matrix. We are of course talking only about square matrices. And correspondingly, a linear transformation or linear operator will be called diagonalizable if the vector space on which it's an operator has a basis in which the matrix of the operator is a diagonal matrix. Alright, so let's now see the exercise. We have a linear operator T on the vector space V such that all its characteristic roots lie in the underlying field F. Then T will be diagonalizable if and only if this condition is true. What is this condition? That if you apply the mth power of the operator T minus lambda on a vector V and get 0, then applying T minus lambda on V will also give you 0. Okay, so this condition is an implication. For a positive integer m, a scalar lambda coming from F and a vector V coming from our vector space, if this is true, then this is true. And the thing we want to prove here is that T is diagonalizable if and only if this implication is true. Okay, so let's start the solution. Now, in order to write things neatly, we are going to follow a notation that we used in the previous exercise also. In fact, let's start with a note about that notation. Writing large matrices is somewhat cumbersome. So the note is this: we will denote a diagonal matrix with diagonal entries by this symbol. Okay, so you may remember that we did something similar when talking about block diagonal matrices. A similar notation was used, so following that notation, we have this notation as well. Alright, so let's now start the solution. So this is an if and only if statement, so we have to prove both ways. Let us first start by assuming that T is diagonalizable. Let T be diagonalizable. Then the vector space V has a basis. So V is n dimensional, so there are n vectors in the basis. in which the matrix of T will be a diagonal matrix. The matrix of T, which of course we write like this, M of T is a diagonal matrix like this. Lambda 2, lambda 2, lambda T, lambda T, where these in F are distinct characteristic roots of T. Remember the condition that F has all its characteristic roots in the underlying field F. However, characteristic roots may not all be distinct. There may be repetitions, and that is why we are writing like this. Also, you can just simply rearrange the characteristic roots by rearranging this basis, so that way the matrix that you are going to have of T with respect to the basis will look like this. All the say first you have the eigenvalue lambda 1, characteristic root lambda 1. So you first have only lambda 1s along the diagonal, and then followed by the copies of lambda 2. You see, in general we write like this. Actually there may be only one lambda 1. That possibility is also there, or there may be really many lambda 1s. All the possibilities are there. And these lambda i's individually are distinct characteristic roots of T. Okay. Now let this be equal to 0 for some m. M here of course it's some positive integer. We do not write that again. It's understood. For some vector v and scalar lambda. What do we want to show? We want to show that v t minus lambda is also equal to 0. Suppose that is not true. Suppose this is not equal to 0. Now you see two conflicting things. One is that a power of t minus lambda, which is t minus lambda itself, when applied on v gives you a non-zero vector, whereas another power of t minus lambda when applied on v gives you the 0 vector. So if you start increasing the exponent, here you have 1, next you can consider 2. When you apply the square of t minus lambda on v, you may or may not get 0. Okay, we don't really know, but you cannot just simply go on having non-zero vectors, because the moment you reach n, you must have 0. So between m and 1 there is some integer k for which this will happen. Hence there exists an integer k such that we have these inequalities, and if you apply the kth power of t minus lambda on v, then you get 0. But if you apply the previous lower power, you do not get 0. This is not equal to 0. Okay. Now we are going to get something from these two relations, namely this. 0 is this, which you can also write like this. On this we apply t minus lambda, and in fact that gives us this, obviously. Okay, now what does this equation tell us? Note that applying t minus lambda to the power k minus 1 on v after all gives us what? It gives us a vector, and that vector is non-zero. That means on that non-zero vector, if I apply t minus lambda, then I am getting 0, which means what? That t minus lambda is a singular linear operator. It's not regular, because in its kernel there is a non-zero vector. T minus lambda is singular. In other words, lambda is a characteristic root of t, but we know what the characteristic roots are. That means this lambda must be one of these. Okay, so let's assume that lambda is some lambda I. So for some I in this range. Okay, so with this information, let us now write the matrix of this kth power of t minus lambda. The matrix is, this matrix is also going to be a diagonal matrix. And the matrix in our notation is going to look like this. It will be somewhat long, even after using this short notation. First we will have lambda 1 minus lambda I to the power k, and like that a few of these will be repeated. As many times as we have lambda 1 repeated, that many times we are going to have this. Then lambda 2 and like that. If one, I just made one small mistake. We do not have commas here because it's a matrix. Okay, and then continuing like that, we will eventually reach the characteristic root lambda I minus 1. I minus 1. From that also we subtract lambda I. A few copies of this. But then after that, those characteristic roots come which are just lambda I. So from them if you subtract lambda I, you are going to get 0. A few zeros. How many zeros? As many lambda i's you originally have in the matrix of T, followed by this a few of these differences which involve lambda I plus 1, the next characteristic root, and then it goes like that, and finally lambda T. So you see that even with our notation we have to write so much. That's why we need this notation. Otherwise you can see that very quickly it will become unmanageable. You won't really be able to write it convincingly no matter how large a board you use. This is one reason that mathematical notations look so compact, and because of that somewhat weird. We do not write things simply because they look fancy. We write them like that out of necessity. Okay, so that's the matrix of T minus lambda to the power k, and matrix in what basis? In that basis of V, where the vectors are V1, V2 up to Vn. Now if we express the vector V as a linear combination of those basis vectors, then now that is also necessary. Also, and say the scalars there are alphas, alpha 1 V1 plus alpha 2 V2 etc. plus alpha n Vn for some alpha i's in F. Now applying the operator T minus lambda to the power k on V is similar to applying the matrix on the coordinate n tuple of V. That is, you can apply the operator on V, that's one thing, and that gives you 0 of course, but you can also apply the coordinate n tuple, on the coordinate n tuple I mean, you can apply the matrix. By that what I mean is this. Zero equals you understand what this 0 is. This 0 is again an n tuple. You can call it the coordinate matrix or the row matrix which corresponds to V, because V is n dimensional. So V is isomorphic to Fn. So instead of considering vectors from V, we can also consider n tuples from Fn. And the association or this isomorphism between V and Fn lets us write a vector V like this, okay, using the coefficients. The basis that we have of V establishes that isomorphism. And on Fn you can apply a matrix, an n by n matrix. And what does that actually mean? It means multiplying such a row matrix from the right side by this n by n matrix. That will again give you another row matrix. And this association, this operation is in fact nothing but T in another form. Alright. So now if you actually do the multiplication, what are you going to get? It may look daunting, but you are actually going to get just what? You see, you are multiplying a row matrix by this diagonal matrix. So this is very simple. What happens is that you multiply, for example, the first element of this row by the first element of the first diagonal element. So that becomes the first element of the resultant row. Second element of the row times the second diagonal element. It's just that. So that way you get this. You won't really be able to write much in between, because we don't know how many of these are repeated. Here, however, we just have simply coefficients, so we write the first element and the last element. That's not a problem though. Because what matters is whatever we are going to get from this, the interpretation is what matters. Okay, so what this equation simply tells us that all these entries of this row matrix are going to be equal to 0. However, some of these entries themselves are 0. Which entries? Namely the ones that correspond to the characteristic root lambda I itself. Here, those entries are also there somewhere. Those entries appear as a block of zeros. So, equating those zeros to the 0, in fact, let me just write instead of 0, let me write more clearly this. So, equating those zeros which correspond to the lambda i's, lambda I, to these zeros, corresponding zeros here, don't really give us anything, 0 equal to 0. However, the other entries are equal to 0. And what does that tell us? For example, say lambda 1 is not equal to lambda I. Okay. Then what does this element being 0 tell us? It tells us that alpha 1 has to be equal to 0. Why? Because this is not 0. And the product is 0, so alpha 1 has to be 0 because we are in a field. A field is an integral domain. So we can write like this. So alpha j is equal to 0 except for those j's how can I write this sentence though? Except for those, or let me straight away write instead of using j, except for those alphas that are coefficients of the characteristic vectors corresponding to lambda I. Do you get what this means? Here you see the alphas as the coefficients of characteristic vectors. Those alphas that correspond to the characteristic vectors corresponding to lambda I are, we do not say anything, we cannot say anything about those alphas. The remaining alpha j's which do not correspond to lambda I in this sense but correspond to some other lambda j's, they are 0. Okay. Hence, now if on V we apply, or let me first show the matrix thing. We will now get this as well. Why? Well, you think of it, those alphas that do not correspond to these lambda i's which you can see here are already 0, and they get multiplied with things like this when you do the multiplication. So you get 0, and the ones which correspond to the lambda i's, there the diagonal entries themselves are 0, but for those entries the elements that we have here which correspond to the lambda i's, about them we don't know anything, but they are getting multiplied by 0 diagonal entries. So ultimately everything is 0. Now if you translate this back into the language of operators, because these are matrices, you get this, i.e. because this, when you write as, you write the vector in V which corresponds to this n tuple which is our small v, and in place of this matrix you just write the operator. Okay, so you get this, but this is precisely what we supposed is not true. But this contradicts our supposition, because we supposed that this is not 0. So our supposition is wrong. That is, we must have this. So our implication has been proved based on the assumption that T is diagonalizable. Now we have to do the converse. Conversely, let the following implication be true for all positive integer m, vector v, and scalar lambda coming from f. This implication. If this is 0, then this is also 0. We now have to prove that T is diagonalizable. That is, the vector space will have at least one basis in which the matrix of T will be a diagonal matrix. So what we do, we are now going to make a claim. We claim that the minimal polynomial of T over F, of course, that's understood, is this. For some distinct scalars do not confuse these lambdas with the previous lambdas. Okay, that part of the proof is over. We do not have anything to do with that now. This is something else. Okay, this is the converse part. So what we are claiming is that the minimal polynomial of T looks like this. It does not have repeated factors. All these lambdas are some distinct field elements. Suppose this is not true. We want to prove this claim now. Then the minimal polynomial is going to instead look like this. For some distinct scalars and positive integers, where MT is say greater than 1. Simply saying that these exponents are positive integers is not enough because all of them may be 1, but one of them is greater than 1. You may ask me why I have chosen only the last one to be greater than 1. That's a simple thing. No, I mean you can, if it really is not the last one, you can rearrange the factors and make it the last one. Alright. Now what do we have from this? You see, according to our supposition here in this part of the proof, this is the minimal polynomial for T. Okay, so now what will happen? Just give me a moment, okay. Okay. So, there will now exist a vector. In fact, let us just write things p of x is the minimal polynomial for t there exists a vector v in V, and again this V has nothing to do with V in the first half of the solution. Such that t minus lambda 1 to the power m1, t minus lambda 2 to the power m2, t minus lambda t minus 1 to the power m t minus 1 t minus lambda t is not equal to 0, but t minus 1 t minus lambda t to the power mt is equal to 0. Why? Why should such a vector exist, and what is going on here? You see, because px is the minimal polynomial for t. So, if you choose any polynomial whose degree is lower than that of px, obviously it won't be a minimal polynomial. One such polynomial is this one. I mean, of course, this is not a polynomial because we do not have x here, but imagine the polynomial where in place of t you have x. You have almost all the factors of p of x here in this polynomial, except the last one is not the entire factor. In place of the last one, you just simply have t minus lambda t. I say we do not have the full factor here. Why? Because mt is greater than 1. The full factor should have exponent mt. Here, however, we have 1. So, something is missing. And that is why the degree of this polynomial, I mean, you imagine x in place of t, is smaller than the degree of p of x. So, this polynomial cannot be the minimal polynomial, and as such, when you substitute t for x, you won't get 0. It won't give you the 0 operator. That means this operator that you are looking at here, this is not the 0 operator, which means that there exists at least one vector v in V on which if you apply this operator you won't get the 0 vector. But at the same time, if in the original px you write t in place of x, obviously you get the 0 operator, because px being the minimal polynomial for t also annihilates t. And when you apply the 0 operator, this is the 0 operator. On V, you are going to get the 0 vector, right? Okay. But this means something has gone wrong. let's see what has gone wrong. But then our hypothesis is contradicted. How? What is the hypothesis? Let me just write something here for explanation. You do not consider this part as a part, I mean it's not included within the solution. What was our hypothesis? Our hypothesis was this, that if there is a vector v and a scalar lambda and a positive integer m, and we have this, okay, then this implies that this should also be equal to 0. But you now have a vector. That vector is not this v. That vector is this. Okay. I mean applying only this part on v after all also gives you a vector on which you are applying t minus lambda t. But you are not getting 0. Whereas on that same vector, when you apply t minus lambda t to the power mt, you do get 0. Now think of this vector in place of this v. So this being 0 is like this second equation, because here some positive integral power of t minus lambda t. What we take here as lambda, that does not matter. M also does not matter, it is any positive integer. This image is 0, but then according to our implication this should also have been 0, but it's not 0, and that is why our hypothesis itself has been contradicted. So the supposition is wrong. What was the supposition? That the minimal polynomial for t is something like that, where mt is greater than 1. No such exponent can be greater than 1. All exponents have to be equal to 1. Hence the claim. That means whatever we claimed there about the minimal polynomial of t has now been established. But now we are almost there, because the minimal polynomial consists of distinct factors where there is no repetition. But before we write anything else though, let's just note that one more time. So minimal polynomial of t for t same thing is this. In f are distinct. So the Jordan form of T is a diagonal matrix. Because of this distinctness, the Jordan form is a diagonal matrix. Because do you remember uh, what we said in one solution about the maximum sizes of the Jordan blocks? They cannot exceed the size of the exponent that you have of the factors in the minimal polynomial for the operator, because here each exponent is 1. So, each Jordan block will be 1 by 1. So, the Jordan block, I mean it is a block diagonal matrix after all, no, that will simply be an ordinary diagonal matrix, but that is it. Then there exists at least one basis of our vector space in which we of course have the Jordan form of the operator T, that means we have its matrix like that, but that is now a diagonal matrix, hence T is diagonalizable. Therefore, T is diagonalizable. Okay, so that is the solution. It was a little long. I mean, the main idea itself is not really that long, but it takes some time to write the things. So that's just it for tonight. Tomorrow we again have analysis, and tomorrow we are going to see the second fundamental theorem of calculus, and the one with which we are more familiar from our school calculus than the first one that we saw there. So that's just it. See you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.